So the Highland controversy was a great geological controversy back in the 1880s when the original geologists came up here, and they always thought that the oldest rocks were at the bottom of the section, the youngest rocks were at the top. And then some geologists came up here to Loch Glencool. Nicol and Lapworth published in 1888, and they were the first geologists to come up here and describe the tectonics in terms of thrusting. In other words, the rocks at the top of the mountain were Lewisian basement rocks thrust over younger Cambrian Ordovician sedimentary rocks of the foreland. And this great controversy erupted, which was finally settled by the great Peach and Horn memoir, 1907, when they did a very detailed map of the whole of the Northwest Highlands and especially the Assynt Window, and they proved once and for all the existence of thrusts. And they're marked by plains of mylonites that we're going to see tomorrow, and they are structures that emplace deeper, older rocks over younger, shallower rocks, and this is what we're seeing here. So if I show you this section at Glencool, this is exactly the picture taken from this spot. It shows the position of the Glencool thrust in red, and this is the stable foreland with the Lewisian overlain by the basal quartzites and the Cambrian pipe rock. Thrust Lewisian on top, and in the very top of Loch Glencool over there, you can see the stack of Glencool, which is made of the mylonites beneath the Moine thrust at the very top of the section. So this is a condensed section of the entire Moine thrust zone, from stable foreland, Cambrian quartzites overlying Lewisian, Glencool thrust putting more Lewisian basement over the Cambrian, going up to the Moine mylonites and the Moine thrust at the top of the section. Okay, welcome to day 2 of the virtual Assynt field trip. So you need to have your guidebooks with you during the whole of this day, as always. What we looked at yesterday on day 1 was the stratigraphy of northwest Scotland, running through the whole sequence along the north shore of Loch Assynt. And I'm just going to recap on what we saw yesterday, because it affects what we're going to look at in the future when we're looking at thrusting in the Moine thrust zone. So we started off down at the Lewisian basement, the basement gneisses. Those were unconformably overlain by the Torridonian sandstones, the red archosic sandstones that form all the high mountains around Assynt, including Sulven and Canisp. Major unconformity above the Torridonian, and this marks the base of the Cambrian Ordovician sedimentary sequence. So the base of that sequence is the basal quartzites, the cross-bedded quartzites, overlain by the pipe rock. This is the famous pipes with the Scolethus worm burrows. The Scolethus is a trace fossil. It's not the actual worm, but it's what's left over from it, the burrow. That was overlain by the fucoid beds, the red, sandy, arenaceous units that indicate a slight deepening lagoonal facies, back to a quartzite facies in the Saltarella grit, and then these are overlain by the Durness limestones. The Durness limestones are dominantly lower and middle Ordovician, and they mark the establishment of a major carbonate shelf on the margin of the Laurentian plate as the Iapetus Ocean was expanding. Now these rocks are all in the footwall of the Moine thrust on the stable foreland. The whole of eastern Scotland is comprised of the Moine schist, the mesomorphic rocks, which are probably the time equivalent units of the Torridonian, but are much more distal facies. And they have been thrust over the whole foreland of northwest Scotland along this structure called the Moine thrust. So the Moine thrust is one of 4 major thrust sheets, and these thrusts are all cutting through the entire stratigraphy that we've seen. So here's the Lewisian, Torridonian, quartzites and the Durness limestone at the top. What I've marked on in blue is the stratigraphy. What I've marked on in red are the major thrusts. So the Moine thrust is the major thrust at the top of the sequence. There's another one, the Benmore thrust, in the middle of the Assynt window that brings up slices of Lewisian basement and places older basement rocks over younger Cambro-Ordovician rocks. This is the cam-more thrust, and the youngest thrust is the Searle thrust. Now it's very important to realise that these thrusts form in what we call an in-sequence piggyback propagation. So the first thrust to form is the one that is the most hinterland dipping thrust. And the youngest thrust to form is the Searle thrust, which is out here, where we're just above us. And these thrusts have to form in a piggyback fashion because you can't move this slice first without moving the hinterland. Otherwise you're left with a big hole, and that is geometrically unreasonable. So the way the thrusts work is that they propagate in structural sequence from the hinterland towards the foreland with time. So in this case, the Moine thrust is the first to move, the deepest to initiate, and the farthest travelled. That thrust propagates piggyback-wise on the Ben-More thrust, and then both of these thrusts are carried piggyback on the lower thrusts. And the final one to move is the Searle thrust out onto the foreland at the structural base of the Moine thrust zone. So notice that these thrusts propagate in section towards the foreland with time, and they follow flats where they follow bedding plane horizontals, and they climb ramps where they cut up stratigraphic section. So the normal rules of thrust geometry are that thrusts put older rocks over younger rocks. They propagate in sequence from hinterland to foreland with time. So it's possible when you've mapped all the Moine thrusts that you can unwind it in time, and that's called a restoration of a balanced cross-section. Balanced cross-section simply means you're balancing it using the known stratigraphic thicknesses and the volume. And as long as you do not lose stratigraphy in the footwall, you know that your thrusts are propagating in sequence towards the foreland with time. So what we're going to do here is walk up to the Moine thrust at the top of the crag, and the Moine thrust is the deepest and the first to move, and that is carrying up deep ductile rocks that form down here at very high strain, and these rocks are called mylonites. Okay, this is obviously a brittle thrust plane. It emplaces ductilely deformed mylonites over heavily crushed Durness limestone. Now most mylonites occur in the ductile lower crustal regions at high temperatures, but in the ductile lower crust the rocks are hotter and higher temperature, more ductile deformation, and they deform by crystal plastic flow, and that produces rocks called mylonites. So here is a sample of the Moine mylonite, and you can see that it has a very strong layer parallel foliation indicative of pure shear flattening and simple shear shearing. So you're taking a limestone or a Moine schist and squashing it and shearing it to produce a highly deformed, ductilely deformed rock. These have very prominent lineations and very prominent flattening mylonite fabric foliations. The lineation is always indicative of the direction of transport. In this case, it's towards the west. So the Moine thrust is emplacing the Moine schists over the stable foreland of Laurentia, which is over there. So this is the brittle fault that is commonly called the Moine thrust, but it's only the latest part of motion on that fault. The earliest part are in these mylonites that have been derived from the deep part of the crust earlier in the sequence. And these deep mylonites have been exhumed along that thrust plane as it's coming up from the deep crust over up into the brittle crust, goes from the ductile to the brittle regime. You go from the ductile mylonite fabrics like these rocks to the brittle faulting. Brittle faults are where you get earthquakes. Anywhere you see an earthquake, that's brittle fracture, where the rock has moved instantly like that. And this is what this fault is here. This is just the latest stage of the history of the Moine thrust that goes back maybe 3, 4, even 10 million years. And these mylonites were derived from much further over to the east, and as they were transported to the west, along the Moine thrust. They were exhumed, getting shallower and shallower as the Moine thrust was culminating up and over. And the final motion of the Moine thrust was folding over the ascent window. And where we are here at Knocken Crag, we're almost directly over the foreland. All of the fold structures that we see in the middle of the ascent window are not beneath us here. They are in the middle of the ascent window to the north of us. And we will see that from a panorama on top of the Knocken Crag in the next stop. Standing here at the top of the Knocken Crag section, and we've got a fabulous panorama across the entire southern part of the ascent window. I'm going to run you through the scenery here and the mountains and the geology from the foreland over in the west to the hinterland in the east. So in the west we have the stable foreland with the big Torridonian mountains of Coolmore, Coolbeg and Stack Polly. These are Torridonian sandstone mountains sitting unconformably on the Lewisian, and on top of all of them are the basal quartzites, the white rocks down here dipping towards us underneath the Searle thrust. And as we swing round, we can see the beautiful mountain of Sylvan with the long ridge and the mountain of Canis. These are both Torridonian outliers sitting on top of the Lewisian basement. Halfway up Canis, you can see the Canis porphyry, the intrusive sill that intrudes into the Torridonian. And then the right-hand slope of Canis is a 10 to 15 degree dip of the basal quartzites. Where that ridge of Canis hits the glen at the bottom, that is the Searle thrust, the basal thrust of the Moine thrust zone. And then on top of that, we have the Camlock clip, which is a little clippen of everything, Lewisian basement, Torridonian, Cambrian, and it's folded and thrust above the Searle thrust duplex. Swinging round from Camlock, we have the big white mountains in the far distance. That's Benmore Ascent and Conival, and those are imbricated slices of basal quartzite above the Benmore thrust. The Benmore thrust is right up at the top of those mountains, and it brings a slab of Lewisian gneiss basement up over the basal quartzites. And in the middle distance, the long black whaleback ridge is the Borrolin. That is the syenite complex that is sandwiched between two thrusts, the Benmore thrust above and the Borrolin thrust below. And the white quarry, you can just see the white scar of the quarry of Leadmore. That is the mesomorphic aureole surrounding the western margin of the Borrolin syenite. That's a high temperature metamorphic aureole composed dominantly of white and green and pale yellow marble. The Borrolin is all the syenite complex, and that is sandwiched between the two thrusts. On top of the Borrolin, the Benmore thrust wraps in around the top of those quartzite mountains, and it brings in the second, the uppermost of the two big alkaline intrusions, the Loch Ailsh intrusion. And that is the dark mountains way in the distance on top over there. And above that is the Moine thrust. So the Moine thrust cuts through right on the skyline, and the uppermost crags that you can see in the very far distance are the Moine schist. Our Moine is Gaelic for bog, and all of the Moine is classically this boggy ground. It's very poorly exposed. So there you have the whole of the ascent window from the Moine thrust to the Searle thrust, very lot of complications, folding and thrusting over the stable foreland. Okay, this is the classic locality of the quartz mylonites belonging to the Moine thrust zone. We've seen Lewisian-derived mylonites, and we've seen calcareous-derived mylonites. These are derived from the basal quartzite which we've seen on day 1 at Loch Assynt in the undeformed state. This shows that the minerals are completely recrystallized. They're much finer grained because they've been subjected to a huge amount of shearing, both compressional shearing and simple shearing. In this case, this outcrop is running north-south, and we know that the transport direction of the Moine thrust was from the east to the west. So if we want to find fabrics that give us a sense of shear indicator, we need an outcrop that is parallel to the transport direction and at right angles to this face. So we really need a face like this. If we find good fabrics on a face like this, there are 2 types of fabrics which are illustrated on this diagram. They're called C fabrics and S fabrics. S fabrics are the schistosity, the metamorphic planar fabrics that forms this prominent foliation plane here. C stands for cisaillement, which is the French for shear. These are the shear fabrics, and the alignment of the S and the C fabrics gives us an indication of the sense of shear. But you have to look in the right orientation. It's no good looking at this face here because it's at right angles to the direction of transport. So we need to find an outcrop that is going in this direction to find a fabric like this that will give us the sense of shear from east to west. And everywhere along the Moine thrust zone, the shear fabrics, the C and the S fabrics, tell us that the transport direction of the Moine schist and the Moine mylonites was from the hinterland in the east towards the west and the foreland. So in addition to the C and the S fabrics that we've seen in the previous localities, which give us a sense of shear of the mylonites, we're looking for these structures here. These are lineations, which are linear structures, and they are aligned along the sense of transport. So I can take a measurement along this, and that lineation is aligned at 280 degrees west, which shows us that the sense of transport direction on these mylonites was towards the west, which aligns with all of the structures that we see in the fold thrust belt and the C and the S fabrics. Right, so we are now in the Altivuling quarry, which is right here, and this is the Borrolin complex, which is one of the 2 major alkali igneous intrusions within the Moine thrust zone. The uppermost one is the Loch Ailge, which is entirely cyanitic, various different compositions of cyanite. But the Borrolin pluton is absolutely unique, almost in the world, and it has a full spectrum of rocks from ultramafic all the way up through various forms of syenite, K-feldspar bearing syenite, up to quartz syenites, the most fractionated part. Most of the summit region here is made of quartz syenite. The purple rocks here are the ultramafics, and these are entirely made of pyroxenes and olivine and biotite, no plagioclase. So they're mantle rocks, and they form vertical intrusions along the margins of the syenite. Also associated with the Borrolin syenites is a unique outcrop of carbonatite, which is a very, very strange rock. It's an intrusive igneous rock composed almost entirely of calcite. And these are common rock associations in alkali igneous intrusions all through the world. And these are extremely important because they're very rich in rare earth elements. So we're now in the pseudo-lucite bearing syenites of this part of the Borrolin complex. The whole Borrolin is truncated along the top by the Ben More thrust, whereas the Loch Ailge is above the Ben More thrust and truncated by the Moine thrust. And the Borrolin has another thrust along the base, where in this region here we can see the high temperature contact metamorphic aureole around it, and hopefully we can get some photographs from Leadbed Quarry showing these very high temperature marbles. These marbles have olivine, forsteritic olivine, clinopyroxene, brucite, serpentinite marbles. They're different coloured, multicoloured marbles, but extremely high temperature. So these syenites are intruded at temperatures of around 1100 degrees centigrade, but very low pressures. So they're very hot magmas that intrude up very close to the surface of the Earth, and they have a big contact metamorphic aureole around them. These ones have both been affected by transport on later thrusts. And looking at the rock textures here, we can determine the relationship between the igneous fabrics and the metamorphic fabrics associated with the thrusting. So on a cross-section, we're looking at this cross-section here. This is the Boreal and Pluton. The ultramafic rocks are along the southern margin here. They are structurally higher than the sole thrust sheet, with all the imbricated Cambro-Ordovician sediments. And this is the Benmore thrust that wraps around over the top of Boreal, the Canmore clip over here, and the Loch Ailsh intrusion truncated by thrust below and above. And finally above it, the Moine thrust, which wraps all the way around the ascent window like that. So the structural setting of these Borealinite, Loch Ailsh syenites are really important, because we can date them. They have metamorphic minerals in and igneous minerals, and uranium, lead, zircon ages from the Borealinite are 431 to 429. Remember, the Canis porphyry was 430, and the Loch Ailsh intrusion also 430. So all of these igneous intrusions, despite the different compositions, are all coming up from a highly strange alkali igneous source deep in the mantle beneath the Lewisian, intruding right up to the surface and then carried on the thrust during Moine thrust event. So this is a example of the Borealinite, the pseudo-lucite bearing syenite that is part of the Borealan complex. And in this rock here we can see it has a magmatic texture. There's no real fabric to it. So this is a classic magmatic texture of an igneous intrusive rock. This rock here has 4 different minerals in it. It has a very black mineral here, which unusually is garnet. It's black because it's a very high titanium garnet called melanite. It has a dark green mineral, which is the clinopyroxene, probably a diopside clinopyroxene. And then it has these big white crystals here, which are called pseudo-lucites. They're pseudo-lucites because lucite is the mineral which is a feldspathoid mineral, and it breaks down at high temperature to nepheline plus K-feldspar plus muscovite. And that's what these things are here. Now these are clearly magmatic. Where the Borealinite is deformed, this is the same rock, but it has quite a strong fabric in it, a ductile fabric where the pseudo-lucites are aligned in this direction. And if my hand is on the planar feature, which is the flattened pseudo-lucite, and if I take a strike and dip on that, I get a strike direction of almost north-south. It's about 20 degrees east of north, and I get a dip of approximately 10 to 15 degrees towards the east. So this is the lineation direction, which marks the direction of transport during shearing of this rock. This strike and dip of the flattened pseudo-lucite is almost exactly parallel to the myelonites on the Moine thrust above and along the strike of the Benmore thrust that cuts the top of this Pluton. So it's more than a coincidence that this ductile high temperature fabric in this rock is parallel to the ductile myelonites and the brittle faults along the thrust planes. So therefore we think that what was originally a magmatic intrusion, during cooling at high temperatures still, these fabrics were flattened and sheared during transport along the Moine thrust system. We're actually structurally below the Moine thrust, so these rocks here are carried on another thrust beneath this complex that we call the Borealan thrust, and the original magmatic textures in this region were superimposed by ductile shear fabrics, still at high temperatures, about 500 degrees, but the original magmatic temperature of intrusion was more like 1100 degrees. So as soon as the alkaline igneous rocks started to cool, they were affected by ductile shearing on the earliest transport of the Moine thrust zone. Now these fabrics are restricted to shear zones, and in some places, if you swing around here, you can see that there are little aplytic dikes that cross-cut some of the fabrics, and they're oriented, some of them are oriented this direction, some are oriented in this direction, but the flattened pseudo-leucites are very prominent parallel to the fabrics in the Moine thrust above. So in conclusion, we think that these syenites were intruded at very, very high temperatures, over 1000 degrees centigrade, up through the whole sequence. They come from mantle melting, very highly alkaline, anomalous parts of the mantle, and the intrusion cuts through the Lewisian, the Torridonian, the Cambro Ordovician, and they come up very close to the surface, extremely hot, so they have a high temperature metamorphic aureole around them. And then as they cool down through 500 degrees, the shearing starts. This is the earliest type of shearing on the footwall of the Moine thrust. And then the whole borrelonite complex cools even further, and it goes from the ductile regime to the brittle regime. So these are the early ductile fabrics, and they are superimposed by late brittle fabrics as the borrelon thrust is transporting the whole complex from the hinterland towards the foreland, from east to west. So on a cross section, this is exactly what we're looking at here. The Altavulin quarry is about here on the borrelon complex, and you can see that the borrelon syenites in orange with the ultramafics along the base are truncated by the Benmore thrust above, and they are carried on the borrelon thrust below, which structurally puts the borrelon complex above the sole thrust imbricates, which is the lowermost thrust sheet of the whole Moine thrust zone. So the ductile fabrics we've seen are actually within the middle of the borrelon complex, and it's a ductile shear zone that is parallel to the Benmore thrust, parallel to the Moine mylonites, has a strike and dip orientation exactly the same. So it's pretty good evidence that this is high temperature ductile deformation superimposed on an original magmatic fabric. We're standing here at the Altavulin quarry, which is in the borrelon syenite complex, and the borrelon is one of these two syenitic intrusions that is within the Moine thrust zone. The higher one, the Loch Ailsh, is truncated at the top by the Moine thrust, and it's carried below by the Benmore thrust, which includes Lewisian, Torridonian and Cambrian sedimentary rocks. The borrelon complex is structurally below the Benmore thrust, and it's carried on another thrust down here called the borrelon thrust, together with its high temperature metamorphic aureole. The purple rocks here are the ultramafic rocks that occur along the southern margin of the borrelon pluton, and these are subvertical sheets which are associated with the earliest phase of intrusion of the borrelon. So in borrelon we have a complete range from ultramafic rocks. These are, the old name is chromaltites, composed of olivines, pyroxenes and biotite, to garnet pyroxene nepheline syenites, and the most fractionated sequence here, the quartz syenites. So we have the complete range here from ultramafic all the way up to quartz syenites. These are very low silica, undersaturated melt. Also associated with the borrelon pluton is one outcrop of carbonatite, which are very, very strange igneous rocks composed almost entirely of calcite. And carbonatites and alkali intrusions are very closely related, and they're important economically because these are very high in rare earth element abundances. So this was intruded up through the Torridonian, the Lewisian, into the Cambro Ordovician at 431 to 430 million years ago, and the temperatures of formation, crystallization of the syenite are about 1100 degrees centigrade, but the pressures are very low as 2 or even 1 kilobar. So they're very hot magmas intruding up very close to the Earth's surface and with a huge thermal contact metamorphic aureole around it. We see that aureole in this western part of the Borrolin complex around Leadbeg quarry. As it's transported on thrust, it has lateral ramps both here and here, so it truncates a lot of the imbricate structures here. And if this was intruded post-thrusting, as some of the early models wanted, we should have seen a huge contact metamorphic aureole around the whole thing, and we don't. We only see it around this part here because it's been faulted out along these lateral ramp systems. Okay, so we are right on the western end of the Borrolin intrusion, the Borrolin syenite intrusion, which is this syenitic intrusion that cuts through the Moine thrust zone and is transported by the Borrolin thrust. So above me here are the marbles. These were Durness limestone, and they've been metamorphosed to very high temperatures during intrusion of the syenite. So the syenite magma was at something like 1,000 degrees, 1,100 degrees centigrade, and it intruded very close to the surface. So the pressures are very, very low, and it cooked up the surrounding rock. So this is a contact metamorphism of the Durness limestone. The highest grade rocks that we've found in this region, in this quarry, contain olivine, forsterite, and pyroxene diopside. So olivine clinopyroxene marbles are about the highest metamorphic grade in the contact metamorphic series. They have been subsequently affected by fluids, and what we see now is late stage lower temperature serpentinization. So this greenish mineral here is serpentine after olivine. It's probably antigerite, and this serpentinization process happened at about 300 to 400 degrees centigrade. So it doesn't record the highest temperatures of the intrusion, it's a later, lower temperature. There's also another very prominent mineral here, which is this bright yellow one. And this is brucite, which is characteristic of the contact metamorphic marbles around the syenite. In the quarry you can see these dikes of borrolinite intruding the country rock. And the country rock includes the basal quartzite and the Durness limestone, both of which are affected by contact metamorphism. So there's not many mineral changes in a pure quartzite, but in the marbles we have high temperature minerals like olivine, forsterite, spinel, wollastonite, and clinopyroxene, mostly diopside. Some of the borrolinites are spectacular here, and we can use this as the evidence that the Borrolin intrusion was intruded up, cooking the country rocks around it into this contact metamorphic aureole. And then it was transported on the Borrolin thrust after the Loch Ailsh intrusion, structurally higher, was emplaced above it. So we have evidence for igneous high temperature intrusion, high temperature contact metamorphism, and thrusting that cuts out the metamorphism on either side.